Hello, Karishma. Hello.
Hello, uncle.
Hello, Karishma. How are you?
I'm fine.
Okay, sorry. I mean, the UK time last weekend changed to 1 hour winter time.
Okay.
Uh,
Yes, sir.
now here still only 10 o'clock. I was thinking
Oh, okay.
meeting is at 11 o'clock. So I was lethargically Sunday. So I was just having coffee and then email came that you joined the meeting. So, okay.
Okay.
Okay. Uh,
So next week onwards, we'll have class uh, at what time?
you have another some other
Yes.
after this one after this.
Yes, yes.
Let's keep it as 10 o'clock. That's okay.
Okay, fine. Okay.
This time is okay for me because I don't have other commitments. So
Okay.
okay, okay. Let me open a Word file. Okay, so we were looking into. Second.
Calculus.
Yeah. Okay. 1 second. Okay, we started with some basics of calculus, right? Okay.
Yes.
Okay. Let me set everything and let us jump into the. So let me first share the whiteboard and recording. Recording is already there, right? Yeah.
Yes, yes.
Okay. Okay. So last time we just started the discussion about the so with the good understanding what is that calculus mathematical tool, then it will be all going very easy and straightforward. Okay.
Okay, yes.
To get an example, physically, okay, the realistically speaking, like let's say there is an object but it is actually above the ground, and let's say we are making an experiment. Consider that, I mean, it could be a fruit on a tree or something like that. Consider that it is just snapping out of the tree and then falling down. Okay.
Okay.
We call that the dynamic starts at that point. Then for all purpose, we say that it is a 0 second. Everything is started happening here. So the whole thing about learning all the subjects like maths, physics, or chemistry, or biology, or whatever it is, it's all about the thing related to that. Physically, what is happening, that is what the physics is dealing with. Mathematics is all
Okay.
supporting the required mathematical model and the tools and everything. So this is a simple example. Let's say a object is free falling. That is, it is snapped out of that. Obviously, it is falling. So there is a reason why it is falling, particularly in the downward direction. So this is like how the Newton has thought about all this whole stuff, right? So that has given all the explanation. The whole physics started from Newton's understanding, and he explained that very clearly using the mathematics. Let's do it in the same way. So what else we know at a time t equal to 0? Let's say there is a height here. Is it okay?
Okay. Yes, sir.
So that is another information we know, because that is going to become, we know that, let's say it start at time t equal to 0 second, and let's say it takes t equal to t final,
Okay.
because we just this is the initial condition. Okay, initial condition
Okay.
for initial condition for independent variable. Okay, independent variable. Okay, because time is always varying, and we know that, but our interest is right now about the dynamics of that particular object which is just started to fall. That's why we use that independent variable for checking whether any other quantity related to this dynamics of this object is just started to fall to go until the ground. Then this become the final time for us. Is that okay?
Yes, sir.
Final time where we may be interested. First of all, even how much time it will take to go down, that itself is a point of interest. Do you get that? The quantity of interest. So that is all it started. So, okay, now we know that definitely there is a height involved, and that height here, let's say this is our from the ground, this point is, let's say we say that this is a height h of, because height is a function of time. Do you understand that? Because it started with height is going to be our h max. Do you get that? At a time t equal to 0, this is going to be h max. Hello?
Yes, sir.
Yeah. Okay, so rather okay, so this is going to be okay, rather h max. I would say that consider that this is a displacement. Is that okay? Use the word displacement.
Okay.
Why I changed it rather than height to displacement, because I want to have the initial condition to be a 0. Do you get that? Do you understand that?
Yes, sir.
Okay, so when we start the experiment, the object has not displaced anywhere. We consider that it is a 0, and when it is reaches the ground, we have a full displacement here. When S is going to be our S of t equal to t final, then this whole quantity become the h itself. You're okay with that? H meters.
Yes, sir.
Okay, so that is how. So this is a point of interest. So we are seeing that as the time goes from 0 time to t final, there is a movement happen to this particular object, and it is going to hit the ground. In doing so, it has traveled a h distance downward direction. So first of all, we know that this is all happening. And how about the other quantity? Let's say this S. This S is a time dependent quantity, right? S is a function of time. Do you get that? Is a
Yes, sir.
displacement is a function of time. Okay, so that is what makes things. The questionable thing is, if something is function of time, we maybe discussed earlier this, but I'm repeating it because we need to quickly understand how the limits and how the continuity and the differentiation, the integration, everything is all connected. Then we can start using the mathematics for that in different function. Is it okay? That is why I'm recalling what we did much earlier. Is it okay? Okay,
Yes, sir.
definitely the S is a function of time. Then we need to look at, we don't know whether it is going to be, there are a lot of scenarios. It could be, definitely, if you put against the time, it could be a straight line. Is that okay?
Yes,
Or it
sir.
could be, we don't know whether exactly, or it could be a parabola like this, or it could be a parabola like this, or it could be saturating like that. Lot of things are possible scenarios. So we don't know really how the S of t is. We get that? That is a question mark.
Yes, sir.
You understand that? So
Yes, sir. Yeah.
if you take this particular case, we are saying that S of t is directly proportional to the t. Is that okay? Then there will be a constant. Then we say that that velocity will be a constant. We get that? So then we will make it as a S of t is actually equal to some constant. Then we know that that constant is the velocity multiplied by time. Do you get that?
Yes, sir.
But how to make sure that this is correct? Do you get that? How to say that which function is correct, whether it is a straight line is the right function for the displacement, or a parabola kind of looking function, parabola, or it could be exponential of t. Do you get that?
Yes, sir.
So we are not sure about that. So that is where the whole calculus mathematical tool is coming into picture. What we are trying to do, let's say it is some function. Okay, it is some function, like it could be anything, it doesn't matter. So all we are going to do is, let's say, take this time. Experimentally, we would be starting from time t equal to 0. Really thinking we may be making some equal tiny small pieces of time. Do you get that? From 0 to 1 second to 2 second to 3 second, we will be measuring how much displacement has happened. Do you get that?
Yes, sir.
So we go for a delta t equal amount, and we are going to say that, okay, I go here and I check what is the change happened is the delta t in the time, and what is the change happened in the displacement itself. Do you get that?
Yes, sir.
So we want to see that what this has happened. This is with respect to, practically speaking, it could be t equal to 0, 1, 2, 3, 4 kind of stuff. But this is for our convenience. We made it as a slices, which is jumping from 0 second to 1 second to the 2 second. So the gap, delta t, we uniformly taken it as a 1 second gap. Is that okay?
Yes, sir.
Okay. But strictly speaking, the t is a continuous variable. Do you get that? Continuous variable. Because it is our limitation, maybe we measured it for every 1 second or every 0.1 second or 0.001 second, that doesn't matter. But we know that it is continuous. Do you get that?
Yes, sir.
This continuity, it is actually asking us, can you let this delta t go as small as possible to the zero quantity? Do you get that?
Yes, sir.
Because if you make a 1 second difference, there may be some change. The change may not be uniform. Do you get that?
Yes,
So
sir.
if you see the, let's exaggerate this. If you take uniform pieces, like bigger pieces of delta t, then the change happened in the S is not same. Do you get that?
Yes, sir.
Different. So if you make it as fine as possible, you go as small as possible. Mathematically speaking, we are saying that in the limit of making that difference in the time go to as close to 0, then we are checking what is the change happened in the S to the change happened to the T. Make sense to you?
Yes, sir.
Okay, so that is what is going to call that as the differentiation of the S with respect to the variable T. That is what the actual meaning is. You know why the limit comes into picture? Because the T is continuous and the S is also continuous.
Okay.
Make sense to you?
Yes, sir.
Okay, this definition is all fine. Now, how to use it in the application point of view? Now take the same example. Let's say the object is freely falling just at time t equal to 0. Then we know that it is going to come to ground. Now we know the displacement itself function of time. What is the, we are questioning what is the change happened to the S with respect to time. Is it okay? Because as we know that this is changing, so we need to check with respect to time what happening. Then we defined this itself as our velocity in the physics. Is it okay?
Yes, sir.
In this particular case, whether the velocity, what is the velocity here? Velocity when time t equal to 0. At the very start, just it is starting, what will be the velocity to begin with? Hello?
Yes, sir.
Have you answered that? Hello? Hello, Karishma, I can't hear you.
Do you know me now?
Hello, yeah. So you got
Okay.
disconnected?
Yeah, I got disconnected. Could you
Okay.
repeat that question?
Yeah, I mean,
It's
this is
breaking.
obvious, right? Now we say that the displacement made by that object is actually time varying. Is that okay?
Okay, yes, yes, sir.
Once it is time varying, then immediately we say that we need to make the delta t goes to 0 and find the delta S by delta t, which is nothing but ds by dt, differentiation of S
Yes.
with respect to time, and we call that as a velocity.
Velocity.
Of course, okay, all good. But take the example what we started with. What is the initial velocity? That is v
0.
0 meter per second. You're okay with that? Okay. And don't you think that it start with a 0 and it is keep changing as it is going down? Is that okay?
Yes, yes.
Then obviously we are saying that this also is a function of time in our example. Do you get that?
Yes.
Okay. So that makes us the next question.
dv by dt.
Yeah, exactly. So we need to
Acceleration.
make the same, whatever the same analysis mathematically we did, we need to look for what is this is. You get that?
Acceleration.
Okay, we understand. We give the understanding and the meaning as an acceleration in the physics, acceleration, but that is the
Rate of change.
exactly the rate of change of velocity with respect to time. So
Yes.
that is you. Then the next question come. Okay, why it is getting accelerated? Do you get that? Because something is acting on that object. That is why it is getting accelerated to go to the ground. Do you get that?
Yes.
So the action is because of, that is why Newton understood and he explained that, okay, Earth itself is a mass. It will have a gravitational field strength, and that is from its center to the surface. It will have a value in the direction to go to its center, which is a value A equal to our G amount of meter per second square. Is that okay?
Yes. Yes, sir.
Okay, and G can be calculated with the capital G, mass of the earth divided by the radius of the earth square. We discussed about that.
Yes.
We did that.
Yes.
Okay, so now that makes the understanding, he just put it as, let's keep this acceleration as a constant quantity. You get that?
Yes, sir.
So with the requirement, there is quantity which is time varying. That is our starting point is displacement, which is obvious. Really, we are seeing that quantity. And then as it is time varying, we look for what is the change happening to that quantity with respect to time. In mathematics, we call that as a differentiation of S with respect to T. As you said, it is the rate of change of displacement with respect to T. Give a name for that for understanding as a velocity. Then we look at the scenario, understood that, yeah, even it starts with 0 meter per second as the velocity, but as time evolve, time change, the velocity is also changing. Then that means we need to ask the question, what is the rate of change of velocity with respect to time? In mathematics, it becomes differentiation of v with respect to t. That we call that as acceleration in physics. Time being, because you know reason why we are considering constant for the g here, because I'm talking from the Newton's point of view. Do you get that?
Yes, sir.
Because the earth is the biggest mass here which is producing it. It is producing from its center, and it is infinite value at its center, and when it comes to its surface, it has gone to this much value. Do you get that?
Yes, sir.
And what is the big difference compared to the center of the earth? This particular distance h is teeny weeny, very, very small. Do you get that?
Yes, sir.
Compared to our radius of the earth. So you just consider that during this dynamics of this particular change happening in the distance, there is no change in the, so the dg by dt you consider as a 0. Do you get that? So that means the g is independent of the time in our problem. Do you get that?
Yes, sir.
Okay, so that is where all starts. Okay, then he started thinking, okay, I know that there is a dv by dt where the thing is a constant, which is our g. Then we could, now we know that a small piece of, if this is the v function looking like, and if you made it as a, we know the knowledge about this to the time variable, whatever the change this happened, this dt, the ratio between the two we know. Do you get that? So
Yes.
what he did, if you want to get back the complete, the v itself, he just, what he did, he just multiplied both sides by dt. Okay. Then this become g multiplied by dt. You're okay with that? For all purpose, I can still keep it as a.
Yes.
But okay, let's keep it as
Yes.
more general a, and we can substitute the g if you want. Okay, so that makes the dt goes to cancel. Then dv is actually equal to a times dt. Then what we need to do, we know the small piece is the same everywhere. Do you get that? It's the same dv. You're okay
Yes.
with? So
Yes.
all we need to do is, you know, this summation symbol.
Yes, uncle.
Yeah, okay. So we need to add all those small pieces and put the limit that dv going to 0. You're okay with that? Because the small piece, we need to go as small as possible. This definition is nothing but the integration of dv itself. You're okay with that?
Yes, uncle.
Okay, so that is what we are going to use it here. So integrate this side, dv is going to be integral of a dt on the other side. Now, let's put the idea, the initial condition also into our thought process, because this side we are integrating our time variable. That means that t is starting point is at 0 second. Is that okay?
Yes, uncle.
And correspondingly, this side is a v variable integration. Then corresponding velocity at a time t equal to 0 was 0 meter per second. Is that okay?
Yes, uncle.
Okay. And we want to know for all the time, meaning as it is dropping down, we want to know how the function v of t is looking like. Do you get that?
Yes, uncle.
So we want to use the t equal to generic t. Then only we will get this general function. Is that okay?
Yes, uncle.
General function of general function for v. So that is why when you put t equal to t, then this will be corresponding to the v of t itself. Do you get that? Makes sense?
Yes, uncle.
Okay, so that is what makes it as our integration of, what is integration of dv? That is, we are adding all the small pieces, we will get the v itself. Do you get that?
V. Yes, uncle.
And with the limit of 0 to v of t. And if you want, we can also put the initial condition as a initial velocity as a u for our. Always we can substitute the u equal to 0 in our particular experiment of some fruit is falling from the tree. Is that okay? So
Yes.
let's keep it as a u, and then other side we can take the a as a constant, and integration of dt will be a t. Then that will have a limit 0 to t. Is that okay?
Yes, uncle.
So this will eventually, you know how to apply the limits, right? The upper limit and the lower limit for the integration. Have you learned that or not?
Yes, uncle. Yes, uncle.
You know that, right? Then this will be
Yes.
v of t minus u
Minus.
actually equal to a of t minus 0. Is that okay?
Yes.
So this is the one which leads to the variable v of t is a function of time looking like initial velocity plus linearly time varying velocity. Is that okay?
Yes, uncle.
Okay. So you see that in the need and the importance of the limit, continuity, differentiation, and integration. Makes sense to you?
Yes, uncle.
Okay. And we did the other thing also. As we now recovered the v of t, which is going to be our u plus at, voila. Then we know the next quantity, which is the starting point of interest, which is ds by dt is going to be our v itself. Okay, the same exercise. Then we say that ds is going to be equal to the v dt. Then we substitute the v in here. Is that okay? Okay, that will
Yes.
look like ds is actually equal to u plus at multiplied with dt. Then as usual, we do the integration on both sides. This side integration is actually equal to integral u plus at dt. Now time t equal to 0. Mostly we consider that initial displacement is 0. Is that okay?
Yes, uncle.
And then when time t equal to 0, we consider the displacement is the function itself. Do you get that? So this will get us s of t is actually equal to, I complete the integration. Okay, this is equal to t. Sorry, you should have corrected me.
Yes.
Okay. So this becomes ut plus of at square. Is it okay? Makes sense to you?
Yes, uncle.
Okay. So in doing these things, we have done few things about the integration. What has happened? We learned when you integrate the variable small piece itself, we recover your variable itself. Do you get that?
Yes, uncle.
And what we did, when you integrate the variable itself multiplied with the small piece of that, what we have done, we have just look from the variable point of view. This is in the polynomial form because the t integrating variable is in the base level and the x power is actually a constant. Do you get that? You're okay with that?
Yes, uncle.
Okay, so this is a question mark because we have idea about this. When you add all the small pieces of the dt, you will get the t. Then how to get to this integration as an answer for this? First, we need to understand what is the thing happening with the differentiation. Is that okay? Okay, let's
Yes.
get into the mathematics of the calculus. So simply we are saying that, let's say there is a variable x, which is changing from the current value x to x plus dx. Then the change happening to the dependent variable y itself would have its own value change from current value y to y plus dy. Is that okay? So we are interested in the ratio between these two, that is dy by dx. Is that okay?
Yes, uncle.
Okay, take it as a case 0. The case 0 itself is going to be, let's say the y of x is a definition, simply x itself. You're okay?
Yes, uncle.
Then if you want to find dy by dx simply mathematically, then use that y value here, then divided by dx. Is that okay? Then this goes 1 to 1. The answer is a 1. Okay, that is why dy by dx equal to 1 is the answer here. Is that okay?
Yes, uncle.
Okay. Also, once we have done the forward thing, like if you know dy by dx is actually equal to 1, then we should know the reverse mathematical operation to recover back our function. If you know this, then we can always ask from this how to recover the y of x itself. Is it okay?
Yes, uncle.
So the mathematically is the same process. Just take this dy by dx equal to 1. Then that will lead to dy equal to dx. Then we just say integrate both sides. This will get us the y is actually equal to x. But when we integrate, there might have been a constant which could have gone away because of differentiation. Do you get that? Let's say the
Yes, sir.
function itself is having a x plus 2, for example. Then if you did dy by dx, what we would have done, it will be d by dx of x plus 2. Then from the x variable point of view, this is an addition. Addition means we can multiply this differential operator with each and every term. That will become dx by dx plus d of 2 divided by dx. Is it okay?
Yes, uncle.
Okay, so now look at here. We are saying that this is 1 because it is factorized 1 to 1. So that is a 1 plus this one, x is saying I am changing from x to x plus dx. But the 2 is a constant. You get that? 2 won't change at all. So that means it is a 0 by, the change happened in the 2 is nothing. That is what 0 in mathematics. Do you understand why that becomes a 0? So
Yes,
this
sir.
1 plus 0 as a 1. So as
Yeah.
there could be some kind of constant that could have been lost during the differentiation. That is the reason we include that when we recover it back as a integration constant. Is that okay?
Yes, sir.
Integration constant. And there are 2 ways to recover that. Either we can go for when we are given an initial condition, when y of 0 is a 0, then we can use that into our final generic answer y equal to x plus c. Then plug it in, then that will give us 0 is actually equal to 0 plus c. That will give us c is equal to 0. Then this generic function now become a very particular solution which we might have started. Is that okay?
Yes, sir.
This is one way to recover the integration constant. Another one is the definite integral. Definite integral. Integral meaning integration of dy equals integration of dx. That is where we say that when x is equal to 0, y is equal to 0. When x is equal to any generic value x itself, then y is actually our y of x. Is it okay?
Yes, sir.
Okay, so that makes us complete the integration. That is y acted upon by the limit 0 to y of x, which is equal to x itself, limit 0 to x. So this leads to y of x is nothing but x itself. So the integration constant won't needed if you have done a limit integral. Is that okay?
Yes, sir.
Okay, with this understanding, we need to go more towards the mathematics of the what are all the different kind of functions that may be available in the mathematics to be used in different application in the physics or whatever the subject we want. Then we can list out, okay, it is not that only the y of x could be only a x. Do you get that?
Yes, sir.
It could be, take the the different case one. Let's take it as y of x is not a single x. Let's say it is a 3x. Is that okay?
Yes, sir.
Then also we can ask the question how to make the differentiation of y with respect to x. Then this will be d by dx of 3x. Okay. Always it is a good idea. What is happening here will take us to the next step. This is a differentiation with respect to x. X is looking at the function. What kind of function is this? This is simply a 3x. What is the meaning of 3x, Karishma? It is a repeated addition. You're okay with that?
Yes. Yes, sir. Right.
Okay,
Yes.
so we need to use that knowledge, thought process. It's not every time we need to do, but I'm saying that that should flash our mind. Do you get that?
Yes, sir.
Then from the x point of view, it is a addition of three terms. Then the d by dx can be multiplied with all of these individual quantity. That is dx by dx plus dx by dx plus dx plus dx. You're okay with that?
Yes, sir.
That become 1 plus 1 plus 1. The answer is a 3. Okay. So this gives an idea. Generalize the y of x. Let's say it is a some constant value multiplied with x plus some other constant. Look, you see, it is automatically become a straight line. You get that?
Yes, sir. Yeah.
Okay, straight line function. Okay, linear function actually. So if you want to differentiate the function itself, straight line function, this will be d by dx of our mx plus c. Is that okay? So now we need to, from the x point of view, it is an addition. So split the addition into two differentiation plus d by dx of c itself. Is that okay? Okay. So now we know that this mx is so many number of x's. Do you get that? So this is d by dx. Then we say this is x plus dot 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 plus x. Every time no need to do that, but I'm just repeating it this time. Yeah. And then this is going to be x is changing from x to x plus dx, asking the question whether the c will change because I am changing c. dc is actually 0. Is that okay?
Yeah, 0.
0 by dx. Is it okay?
Yes, sir.
Okay, so now this is going to be, we can just say that this is dx by dx plus dx by dx plus dot 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 plus dx by dx. Then this is whole thing will be plus 0. Is it okay? This becomes,
Yes, sir.
and when we count how many of them, this is m of them. Is that okay?
Yeah.
So the repeated addition of same quantity can be written as a m dx by dx. Is it okay?
Yes.
So that will go 1 to 1. Answer is a m. That is the reason whenever we differentiate some constant multiplied by the differentiating variable itself, we just see that this multiplication has two operands. One is a constant with respect to the differentiating variable. That could be taken outside the differentiation. This is another way to look into it, but that is because of this is what the actual thing is happening. Is that okay?
Yes, sir.
Okay, so that will become a. We get that?
Yes, sir.
Okay, so like that, we have to keep using the basic understanding knowledge about the mathematical function, what we are differentiating, and that will recover us. So, okay, let's get the complete picture here. Now, we know dy by dx is actually equal to m as an answer. If you want to recover this for what is y of x itself, we always go for the integration. You are okay with that?
Yes, sir.
Integral dy will be equal to integral m times dx. I just rearrange it straight away. Now from this side is an integration with respect to x. That means m is a constant from the x point of view. Now we can take it outside the m. This is one way, but actually what is happening, this is, you should know that this is actually integral of dx plus dot 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 plus dx. And if you count them, there are m of them. Do you get that? And
Yes.
it's split into m number of integral dx, small pieces. Do you get that? This is count is m of them. This is what written as m integral dx. You're okay?
Yes, sir.
That is actually m integral dx. So that is going to be our, this will give you recover the x, mx, but the integration constant should be there. So that we recovered our function. Is that okay?
Yes, sir.
So now we have gone to the x with the power 1 only. Let's jump into the next possibility. What we are saying, let's say consider the function is our x square. Obviously, right? When x is multiplied with itself. So the procedure and the understanding is the same. We are going to differentiate the x square. Do you get that? With respect to x. So now from the x point of view, what is this thing? This is nothing but x is multiplied with itself 2 times. Is that okay?
Yes, sir.
So from the x differentiating point of view, both the quantity which are getting multiplied, it's are related to the x. In the previous case, it is an addition. So we just split into 2 possible addition. But now it is a multiplication, meaning this is actually x dot x is actual meaning is x plus dot 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 plus x. If you count how many of them, there are x of them. Do you get that?
Yes, sir.
In the previous case, the quantity, how many times it was repeatedly added was a constant. Do you get that?
Yes, sir.
So that is the reason we could do that. But now the quantity which is repeatedly added itself, both the quantity is also related to our differentiating variable. The number of times it is getting added also is the differentiating variable. Do you get that?
Yes, sir.
So we cannot get the x outside the integration. What we could do, simply, this is an example. I might have told you earlier. It is like it's a sheep farm. If you go to a sheep farm and if you want to count how many of them, we will keep one aside and we count the first one. Do you get that?
Yes, sir.
And then continue counting with adding with keep the other one aside and differentiate the other. Is that okay?
Yes, sir.
So this is the first quantity and we differentiated the second quantity. And then continued with, we kept the second quantity outside and differentiated the first quantity. You catch that?
Yes, sir.
So that will become x plus x, which is actually 2x. Is that okay?
Yes, sir.
So if you do that for y of x as a, okay, let me do the integration. So now we know dy by dx is actually our 2x. So if you want to recover the y of x itself, what to be done? We need to first of all rearrange the whole thing. Is that okay? 2x dx. Okay.
Yes, sir.
Now we say integrate the dy. Other side will be integral 2x dx. From the x point of view, this is a multiplication going on. One of them is a constant. Then it is okay to take it out, but we cannot take the x outside because that is the dependent on the differentiating variable itself. So this side will become a y. This is actually equal to 2 integral x dx. Is that okay?
Yes, sir.
But we know that we started with the x square. So eventually we are looking for this answer to be a x square. Do you get that?
Yes, sir.
2 integral x dx is actually equal to x squared. So that means integral of x dx is actually x squared over 2. So what has really happened when we, okay, let's take it as such and I will explain you in the next to go. Is that okay?
Yes, sir.
Y equal to 2 times multiplied by x square by 2 and there should be an integration constant and this thing is going to be 1 to 1, then y equal to x square plus c. We recovered the function itself. You're okay?
Yes, sir.
But if you go for d by dx of, let's say the y is actually equal to x cube. Is that okay?
Yes, sir.
Then what will happen if you want to find dy by dx? D by dx of x cubed differentiation, that will be d by dx of x
Dx.
multiplied with x. You're okay with that? So we keep two of them aside and get the job done with the very only one. Do you get that? Because
Okay.
we know exactly this is the only thing. All other thing has to be derived out of that using our mathematical knowledge. Is that okay?
Yes, uncle.
Okay. So that means plus x dot x dx by dx plus x dot dx by dx. Then we say that there are three of them in the form of x squared dx by dx. Is it okay?
Yes, uncle.
So that makes our answer is 3x squared. So by the look of it, it looks like when you have a function, generically a polynomial type, x powered something like a n, all we need to say that if you are differentiating a function with respect to d by dx of xn, by the look of it, understanding is differentiating variable is x and the function what we are differentiating, the base level is that variable, but the power of that is a constant. Okay.
Yes.
This kind of function they are called as polynomial function. Polynomial function. Is that okay?
Yes.
Function in x, which is also our differentiating variable. You get that? Which is our differentiating variable. Only in that case, we say that it looks like the power n comes to the as a coefficient and the current power has gone by one value down. Is that okay?
Yes, uncle.
That is what has happened in every case if you do that. Okay, so that we can take it as a more generic, straightforwardly like that. That is the reason. So it looks like there are two things happened. One is the current power has come as a coefficient and the power got reduced by 1. So that is the opposite way. When you integrate x dx, we need to do the reverse process. The power has to be, current power is a 1. So the current power has to be increased by 1 and the new power has to be divided. Do you see the connection between the two? Is that okay?
Yes. Yes,
So that
uncle.
will be with the c. That is why it is a x square over 2 plus c. So generically, we can write, if you integrate polynomial function like x powered n dx, the checkpoint is the differentiating variable is x. By the look of it, x is in the base level and the power is a constant. Then only we can say that whatever the current polynomial power can be
Plus 1.
by 1 by
N.
power has to be divided plus c. Is that okay?
Yes, uncle.
Okay, so I think you are okay up to here. Is that okay?
Yes, uncle.
So in doing so, we learned one more thing. What is that? Is whenever we have something like d by dx of multiplication of two quantities going on. So from the x point of view, in the multiplication, both of them are related to x. Do you get that? In that case, we kept one aside and differentiated the other, plus we kept the other aside and differentiated the other. We get the answer. Is it okay?
Yes, uncle.
We can generalize this. What the meaning is, let's say we want to differentiate two functions. One is a f of x multiplied with another function g of x. Is that okay? This is similar from the x point of view. This is nothing but a multiplication. Is that okay?
Yes, uncle.
Both of them are related to our differentiating variable. Makes sense to you? That
Yes,
means
sir.
what? The sheep counting. Keep one sheep aside and get the differentiation done with the other sheep. Is that okay? Other function.
Then add.
Add. Continue, get the job with the other guy. Is that okay?
Yes, sir.
P f of x by dx. Okay. So this people call that as a kind of product rule. Is that okay? Product means multiplication and we call that as a product rule. Is that okay? But actually, this is happening because differentiating variable is the function of both the quantities which are getting multiplied in the operand. Is that okay?
Yes, uncle.
Okay, so that should be the idea. So don't just use the wording as a product rule. Is that okay?
Yes, uncle.
Makes sense to you? So
Yes, sir.
that is quite easy for that. So let's say if you, okay, let's do the other one also. Let's say if I have d by dx of two quantities getting divided. So one is f of x over g of x. Is it okay?
Okay.
Okay, this can be understood because division is simply the inverse of the multiplication. So this could be understood as f of x multiplied with g of x power minus 1. Is that okay?
Yes.
Makes sense to you? Because the g
Yes.
power is a 1 in the denominator. Okay, so now we can use the same, the sheep form. Like keep the f of x aside, get the differentiation done with the our g of x powered whole powered minus 1, plus keep the g of x whole powered minus 1 aside and d by dx of f of x. Okay.
Yes.
Okay. So now tell me, okay, now tell me how to differentiate this. From the x point of view, this looks like a some function which is related to the x with power is a constant. Do you get that?
Yes, sir.
So this looks like a polynomial kind of thing. Do you get that?
Yes, sir.
Then what we need to do? We need to put
Minus.
minus 1 is the coefficient, and whatever the current power has to be reduced by 1. You're okay with that?
I already minus 2.
Yeah,
Yeah.
minus 2 actually, but it is a minus 1,
Yes.
minus 1. I write it more rigorously so that we know what is happening. And
Okay.
we need to still do the differentiation of the function itself with respect to x. We should not
Yes.
forget that. Is that okay?
Yes, sir.
Because that itself need to be dealt with,
Yeah.
because that is the main sheep. Do you get that?
Yes. Yes, sir.
Okay. And then this one looks like 1 over g of x, and this will be d by dx of f of x. Is that okay?
Yes, sir.
So now this will become minus f of x over g of x whole squared. You get that?
Yes, sir.
Okay. And then this thing is going to be, and then we are going to have this guy. Okay, this is another form is, there is another form to write this as a g prime. You're okay with that?
Yes,
Because
sir.
g
Yeah.
prime is actually defined as dg by whatever the variable we are interested. It could be x or it could be y or z, but doesn't matter. But it is a differentiation of one particular variable, what the f is dependent on, I mean g is dependent on. Is that okay?
Yes, sir.
So plus 1 over g of x f prime. Is that okay?
Okay.
So let's write the positive quantity first. That will be f prime by g minus f g prime by g square. Is it okay? So now
Okay.
take the denominator common. That will become g f prime minus f g prime. Okay, so this become a quotient rule. What they say, if something like a f over g, both are dependent on the independent variable, if you differentiate once, you need to make the denominator squared, and then the denominator multiplied by differentiation of the numerator minus the numerator multiplied by the denominator function differentiation.
Yes.
This called as a quotient rule, but this is actually the product rule for functions are getting divided. Is that okay?
Okay. Okay.
Quotient rule. Okay. So now with this in the idea, I will give you like basic thing, like we need to understand what is integration of e power x dx. Is it okay? Also the differentiation of e power x dx. Now, when you look at this, x is the differentiating variable, but the function what we are differentiating, the base level is a constant. You know, e is actually approximately 2.732 and is an irrational number. You know that, right? Some constant rise to the power of x, and x is our variable. Is it okay?
Yes, sir.
Okay. Only for this case, we get exactly the same answer. Is that okay?
Same thing. Yes, sir.
Okay, I stop here because you have the other tuition. So we will discuss about that in the next session. Okay.
Yes, sir.
Is that okay?
Yes, sir.
Okay, Karishma. Take care then. Bye.
Thank you.